Good evening, Taylor Tots. As promised, we're going to do a gas law video this weekend. I apologize, this is actually the third time I'm shooting this video in the last hour, so I'm hoping this is the third time is a charm, but let's just get right into it. So the first thing that I did want to review with you is the 4 parts of KMT. Now, KMT is extremely important because it's going to help you answer essentially the free response questions. What is happening with gases in the real world? And there's some stuff we haven't talked about yet with that, and that's okay. However, these 4 things, and I know it's not the full KMT law written out, I just drew it so you could put it on the page. This is really the essence of what is going on with gases. The first part of KMT is that gas particles have absolutely no volume and they have no plus or minus forces. You see, for example, if I have this little dot that's right here by my finger, let's even say that it's even smaller than that. I'm cutting it down to size a little bit. Would we say that that dot has a volume? Well, that's right. It doesn't. And again, because gas particles are so itty bitty little small, we essentially say it's 0. What this is actually going to end up doing is it actually is going to make the math a lot more complicated. But again, because they're so small, we can assume it's 0. And again, just like we did in class, and again, I got this cool little game set that I played with a while ago in college. I kind of just wanted to whip them black out. You see, normally, if you have magnets, say, and let's say we have a black north and a south that's white, well, if you have 2 positives and negatives, you're going to put them together and they're going to stick together. Again, that's just how plus and minuses work. However, if we had 2 souths, they're going to repel. They're not even going to want to get close together. Or if they have some norths, well, they're not going to want to go together either. Well, that's actually a really big deal because normally that's how things work. Gases do have a charge. We learned that throughout the 4th unit, the 3rd unit this school year. They do have a charge. That's why reactions work unit 5 and then unit 6. However, because gas particles are so small, we assume that even if there is a plus and minus, again, the 2 different colors, they literally just glance off each other. Just like in class, right? Imagine trying to give yourself a hug, but you're going really fast. Like, it's not going to work. Again, I'm jamming my thumbs enough times today to know that it's not going to work. Again, slow-mo gases might be able to hug and keep going, but gases can't stop. So they're going to really try to just, not really going to do too much. Again, just remember the example. I know we all had people in class who were gracious enough to give us examples and run at each other. But again, it's really how it works. The second thing is gas particles. Gas particles move in straight, unpredictable motion. For example, this little dot starting here throughout all these motions ends up over here. Well, I could have done this too, couldn't I? I could have gone here. I could have gone there. I could have gone here. And then maybe I could have got to this point. Well, essentially, gases are just going to be like one big ping pong game. They're just going to keep bouncing off each other in straight lines until they get to a location that is going to be essentially where it's at. Again, it's going to be random. For instance, think in your head today, where was I today? Mr. Taylor, where was I? All right, here's the thing. I was in Batavia. Then I went home to Cary. There was a car accident that blocked my way back home to Batavia, so I ended up going to St. Charles, which led me through Geneva and brought me back to Batavia, where I've been for the last few hours. Now, odds are none of you could predict that that's what happened to me today. None of you could predict that I would have spent time in St. Charles or Geneva today, and frankly, neither could I at the beginning of this morning. I wouldn't have been able to tell you that I was going to be in St. Charles and Geneva for a little bit. But again, that's the random predictability of particles. And again, I'm going to take different ways there than you might. Again, I know 4 or 5 teachers that live in Batavia that teach at East Aurora. We all take different ways to the high school. Again, kind of think of it like that, and I think you'll be okay. Now, the third thing. The third thing is going to be those elastic collisions. Now, this might not be the best example in the world of this, okay? And I'm just going to kind of make sure that you kind of get it. But I got 2 pairs of gloves, okay? These are going to be our gas particles. Again, I just have 2 different colors just so they stand out. And we're going to pretend that these are our gas particles, again, these little game pieces. Again, one black and one white. Well, here's the thing. Elastic collisions, there's no energy loss. They literally just bounce off each other, kind of like a pool game would. They just hit off each other and they just go. Now again, in a pool game, well, they slow down because of the felt. And again, in the real world with gases, that doesn't happen. For instance, in the real world, elastic collisions are going to be like this. Again, it could come out at you. Ooh, a bug. Ooh. This is elastic. Again, nothing's happening. They're literally just bouncing off each other. Here's an inelastic collision. Gas particles do not do this. As you can see, and I'm just going to hold these here and make sure that you can see, so I apologize. Give me a moment. They're smushed. Well, when you smush the things together, they lose kinetic energy. There is an energy loss there. Again, like 2 cars colliding, all that energy is going to go whoop into the car. It gets released, and the cars stop after a car crash. Well, again, because of these gloves, again, if I'm going full force, and again, I was trying to push these together, these gas particles, as hard as I could, well, these guys are going to smush together, or again, smush together, and the energy will be brought in. Again, there's going to be no smushing with gas particles. They're literally just going to bounce off each other, just like this. That one's the one that students normally miss, but again, hopefully not too bad. And then the last part is going to be kinetic energy depends on the temperature. And for this, I think I have a cool demonstration. No pun intended. Now, here's the thing. You have a car. Check out my drawing skills. There's a car, there's a car. And then you have another car. Well, here's the thing. The blue one is going to say be a cold car. Okay, this car is going to be moving slower. So this car, we'll say, is going at negative 20 degrees. And we're using Celsius just so we can talk. Okay, I know Celsius isn't any good, but we're going to just use it so we can talk about things. And we'll have this one at 100. Which car do you think is going to move faster? Or which one do you think is going to have the more energy? Well, as it turns out, 100 degrees Celsius might end up working. We'll just say that's 100 miles per hour. And we'll say that the negative 21, we'll say that's 20 miles per hour. Well, as you can imagine, what car do you think is going to go further and have a little more force to it? Again, if you're getting a car crash, you're going to want to be with a 20 mile per hour car or in a car crash with a 100 miles per hour car. And the answer is going to be the 20, okay? Well, again, the more kinetic energy you have, again, I'm just going to write summer. And this one will be like winter. Again, you have more energy normally in the summer. So this one wins. And there's going to be less energy when it's cold. Again, I know this doesn't hold true per se. I'm one of those people who likes the winter more, so I'm a lot more active, I'd like to think, in the winter. But again, gas particles work the same way. The more heat they have, the more energy, well, the further and faster they're going to move. And those are the, again, 4 parts of KMT. I hope this really helps. One of the things that I'm going to do now is I am going to erase the video. I'm just going to kind of zoom in a little on the half, pause it for a second, zoom in on this, pause it for a second, just in case you wanted to pause the video and write some stuff down. And then we can go into the gas equation, so on and so forth. I always do that the wrong way, I'm sorry. Getting the first 2? the second two. And we can kind of go out from there. And one of these times I'm going to hit this, right? All right. And let's kind of go out for a little bit. Okay. So here's the thing. Besides having a glove, which can now work as an eraser, let's talk about the actual gas laws that we've talked about so far. We have talked about essentially 5 different gas laws. Now, I'm only going to cover 3 in this video. Okay, I'm going to leave combined out of this. Combined is not going to be in this video. I probably shouldn't even draw that symbol. And that's because I'm just going to focus on the basic 3 right now. And those basic 3 are Boyle's, Charles, and Gay-Lussac's. Again, it is very important that you know these equations because they're very, very, very helpful to you. Again, Boyle's, potatoes violently. Charles watches TV. And Gay-Lussac's, well, he drives a PT Cruiser, or he physically trains. This one, as you can see, which is very, very important, has no temperature. This one has no pressure. And this one has no volume. And this is really, really going to help us out with these problems. Essentially, when you're doing your homework problems, if you notice that there's no temperature, or if it says that the temperature is constant, that's probably a huge hint to you that you don't really need to worry about this. Again, a constant temperature, I believe there is a homework problem where I just say, oh yeah, the temperature is 15 degrees, and I say it stays at 15 degrees. Well, if I say it stays at 15 degrees, you don't have to worry about that one. So that one's going to be a Boyle's law. And we can go from there. Again, these guys are going to be really, really important to you. Again, the hints really are, look at what's not there. There's no temperature with Boyle's, there's no pressure with Charles, and there's no volume with Gay-Lussac. Again, those are essentially the equations that you can use. And then again, the practice problems just kind of come with practice. The only other thing I want to show in this video, because again, I don't know how long it is right now. I hope it's not too bad. Again, I'm just going to check to make sure you can see everything. The one thing that we do need to talk about really quickly, I'm just going to go back and pause for a second, just in case you wanted to see, are the STP conditions. You know what? I'm just going to write that right above here, just in case people still need this. STP conditions are a big deal. STP conditions are against standard temperature and pressure. That means everyone is on the same page. All scientists try to do things under those conditions. And the temperature part, that one is going to be 0 degrees Celsius, which equals 273.15 Kelvin. Again, you know the Kelvin number is more important. But again, I want you to see this just so you know, because it is useful when you're trying to figure out in the problem, oh, did the temperature actually change? And pressure, that's going to be 1 atm or 101.3 kPa. These are really going to help you out. Again, if the problem just says pressure and it says STP and it doesn't tell you what pressure to use, you get to pick. You want to do ATM or KPA? It doesn't really matter. Unless I ask specifically for a pressure, that's an ATM or KPA, you can choose. Which again is really, really cool if you think about it. I do want to show you a conversion really quick with that, so I can erase this, I think, finally. Using the white glove, which I shouldn't have, but that's okay. That works out. Again, if I had 17.38 ATM, and I want to go to KPA, or if I want to go to, I liked a joke I heard in class about DJ Khaled's favorite number being 11, because it's another one. I hope I don't get in trouble for that. Let's have KPA, we'll figure out that into ATM. Well, all you have to do, 17.38 ATM. We don't care about ATM, so that goes at the bottom. Care about KPA. Again, we're just grabbing our conversion factor and bringing it down. Or here, again, we don't care about KPA, so we put that at the bottom. Again, conversion factor, we bring that down. We do not care, so it cancels out, and you're left with your answers. I'm not going to solve those for you because you guys can solve them for yourself. Again, I hope this video kind of catches us up a little bit. We're going to talk about the big gas law this next week, which is called the ideal gas law, and that's going to throw a curveball into things, but it's not too bad. Again, please let me know if there's anything in the video that was confusing or anything like this. I hope this one downloads. I hate to do this a fourth time. But again, hope you enjoyed the video. Peace, bro. Out. If I can hit the button. I don't even know where the button is. Awkward ending to the video. First person to say that there was an awkward ending to the video gets 1 point of extra credit on the homework. Later. Bye.